Um, so today I'd like to talk about Kotlin and the speed of Kotlin. Uh, why I would like to talk about this. So I like to crack jokes at Java that it's slow, right? Because it's in JVM, it's an interpreted language, and it's just like a source of fun, among other things about Java. But the truth is that currently, today, Java or JVM is really a good choice for backend applications and other targets that it's trying to get into, also Android. And if you're ever in need for some arguments or data about why it's actually true, then I would like to present some. So let's get on the same page. We know Kotlin, right? That's where we are here. And Kotlin has multiple targets, so-called compiler backends. So this was already mentioned in the previous presentation. There's Kotlin JVM, which uses the hotspot tracing interpreter, or most of the time. This is what is included in OpenJDK and the Oracle shipping of JDK and most of the JDKs. Then there is Kotlin Native, which is a compilation of Kotlin into native code through LLVM. And then there is Kotlin JS, which transpiles to JavaScript. And then you can run it, for example, in Node.js, which runs on the V8 engine, which is also a tracing interpreter. So, what is a tracing interpreter? First and foremost, it's an interpreter. So it takes some kind of bytecode or some kind of representation, which is not directly machine executable, and it translates it at runtime. So this is there's some overheads to running the code on the at runtime at the point that it's trying to execute. But it's also a just-in-time compiler. So when the code runs, it's looking at how the code is running, it's looking at some properties, and it's compiling just in time, just before the execution in real time at runtime. This is very time constrained, obviously, because you're running the application and it's just then that the compilation is happening, as compared to ahead of time compilation, which happens when you're developing before you ship the application. There you have plenty of time to actually compile it. Uh, what a huge benefit this has today is that it can perform something called profile guided optimization at runtime. So profile guided optimization is looking at how your program is running, looking at what inputs are, what is happening inside the code uh, with actual inputs. So if you have a server with actual requests, what code is running the most, and compiling or recompiling, optimizing the code in such a way that gives preference to these code paths to optimize them better. If you have some branching, some ifs, then it's going to uh, change the likeliness of taking or not taking the branch and so on. So this information is really beneficial because it helps us specialize the application. It gives us huge benefits in speed and performance. Uh, and what the tracing interpreter means is that it traces a hot path to the program. So it looks at the execution of the bytecode. It sees some kind of a hot path, so code that is executed often or that takes a long time, and compiles this bytecode, this previously interpreted code, into some kind of like native code. So basically, as if you compiled it ahead of time. And then it can apply the profile guided optimization to this compilation. What this needs, what are the trade-offs? So obviously it needs warm-up. It needs time to collect the statistics, the traces, to know what is happening. But also it can optimize beyond ahead of time possibilities exactly because it has that runtime information, because it has that knowledge that you do not gain while you are developing ahead of time. When you're doing profile guided optimization with ahead of time compilation, you need to have inputs which are representative of your real life deployment. So you would have to ship your application, look at what's coming in, collect information about it, then go back to development and recompile your application and then ship it again. And this can all happen dynamically at runtime uh, in a tracing interpreter, right? So we got to go fast. Uh, and also there are some guards to trigger the optimization. So if you were doing this manually, if you were like saying, okay, so if input with number 5 comes in, I want to do this, then you would have to also handle all the other inputs. You would have to specialize manually. This is handled all inside the JVM, the tracing interpreter in the V8 for JavaScript as well. So this is all happening transparently thanks to the engineering that is behind JVM and other tracing interpreters. So I'm going to go straight to some benchmarks. The next benchmark, I was benchmarking a matrix projection operation. So I have a matrix of numbers. I multiply a vector by this matrix. Very common in math, very simple. There is some million rows. There is 128 integers per row. So this is prime opportunity for vectorization, uh, for a huge speed up. And then I collect some statistics and show it to you. So here we have some initial results. On the x-axis, we can see the implementations that I benchmarked. They are all somewhat equivalent in what they do because it's a simple operation. And on the y-axis, it is a logarithmic scale. We can see the average time that it took to run on this input of a million rows and 128 elements per row. And so we can see on the which side is that? Rightmost, leftmost? I don't know. Rust is the fastest. This is Rust specialized. So specialized means it's the manual specialization I talked about. It's manually assuming how your inputs are going to look like and coding for that specific path. So this is something you never do. Then we have C, which is a real life representation of how you would write the code. And then we actually start seeing Kotlin, right? And the difference is not that huge. I have two flavors of Kotlin here: unboxed and boxed, or without the word unboxed. This means whether I use the boxed integer type that is native to JVM and sort of in JavaScript as well, or whether I used the unboxed native. Uh, in JVM, it's an array. In JavaScript, it's like int buffer. In Kotlin is also in the buffer, but the point is that it doesn't use the boxed types. As we can see, for even when we compile Kotlin to native, but we are using the XS pattern that is used in JVM. So we are using boxed types. Everything's on heap. Everything's memory. Everything's heap allocated. It's terrible for performance. So the first takeaway here is that JVM is actually great at what it does, but that should be no surprise. And on this next slide, I have graphs with more information about the runs. So I cut out the slow runners because those are not really important. On the x-axis, we see the runs as they were progressing, so the number of the run. On the y-axis, we see the time. This time it's a linear scale. The gray lines are arithmetic means of the time it took, and then there are standard deviations in sort of like transparent color. And as we can see from this graph, this is an interesting graph because we both see the warm-ups that is before the dotted line. So this is the warm-up that I'm talking about. In JavaScript, it's very obvious. In the other languages, it's much less obvious. And we see that there wasn't much jitter. We see that JVM, Unboxed, and C are very close together in this very simple hardware-bound operation, which I think is a pretty good argument in and of itself, because we are talking about something that C is supposedly good at, like raw operations, raw throughput. But we're seeing JVM doing the same thing, no problem. And then I have another benchmark, which is going to be, I think, more representative of a real world application. And this was in my university course. We had a competition. We were programming Wordcount servers. So there's a server, it listens on the TCP socket, it receives some kind of protobuf message, which it has to decompress, then split by white space or by, by white space, and then it throws these words that it extracts from this long message into a hash map, counts number of occurrences, and then returns the result. So there is some network communication. There is some protocol to parse. There is some decompression, and there's, let's say, the core algorithm or the core logic is a hash map and hashing of some strings of some average length. So here the measurement was the minimum completion time. This was the criterion for the competition, for the student competition. And the interesting part here is that the best JVM implementation was better than the best native code implementation. And across the board, we can see that everyone from the JVM world or from the JVM implementation, every single one of the JVM implementation passed the cutoff, which is 10 seconds, the dotted line, whereas the C or Rust implementation did not always pass, and there's a huge gap right there around the 25 mark. So what the takeaway here is that for students or people who are maybe new to the language and are taking a course in software optimization or software efficiency, it's much easier for them to write an efficient piece of code in a JVM language, in an interpreter language, which does much of the optimizations for them than to do it manually. And I think this is true in the real world as well, because when you're writing in a native language, you have to do the optimization, the specialization yourself. And this specialization basically comes free in the interpreted world. So if this is representative of a real world application, then these results are telling you that it's a good idea to use JVM for many things. So to summarize, JVM is very optimized for its access pattern. So it's a stack machine. It has a heap, boxes stuff. The same pattern for the Kotlin native was um, JIT has come a long way ever since it was created. This was decades ago, but today it can perform optimizations that are not feasible in at the head of time compilation. It can do the profile guided optimization, as I said. Uh, it can see things that you as a programmer cannot see ahead of time. As a developer, you do not see the real life inputs. You do not have the sample of what is going to happen in production, but JVM does, and JVM can do it for you. Uh, of course, short running code doesn't benefit as much. This is the warm up time. It takes some time to run, but that is the primary way of running backend servers. You run it once and leave it running in production until it crashes or you deploy a new version. So the idea is that this all is within the parameters. This is all optimal. And the more complex your algorithm is, the more it favors a JIT, because specialization is very beneficial. Knowing how your input is going to look like, knowing the shape, knowing the size of the input is really beneficial to optimizing in today's world, in today's computers, hardware, or to get native code. And JIT can do this dynamically. And it can do it reactively at runtime. When your inputs change in half a year, you don't have to recompile your application with new samples. JVM does it. So I hope that was beneficial for you. I hope it told you something interesting about why JVM is a good choice for these applications, JVM or any other tracing interpreter. But since JVM is the most widespread, then I think it makes sense to stick with it. So thank you, and I welcome your questions. There is a question. Yes, I looked at Loajit. Unfortunately, I couldn't get it to be fast enough. I did the matrix projection benchmark, and it was about 200 milliseconds. So if we look at the graphs, it would be somewhere above the Kotlin JS unboxed, about 200 or 300 milliseconds. I don't have the graph here, but yeah, I was expecting more from it, to be honest, because it's really like it has a good reputation. But
Okay, thank you.
so, any other questions from the audience? Yes.
And
you repeat the
okay. The question was if you have some data like comparison between different versions of Java because they claim it's faster with every release. So if you can confirm it,
Oh,
or if you have, sorry, the follow up, if you have comparison between different JIT compilers, I don't know, like GraalVM or JDK and so
yeah.
I'm curious
So
there.
as for the first part, no, I only tested Java 17, OpenJDK 17, the version I already had, because I was trying to more compare between the languages than to compare between JVMs as in as itself. Um, for the second part of the question, no, I only focused on hotspot because recently it is the most widespread. Even the J9, I think it was, that was previously more widespread. It's not so widespread anymore, as I found out. And I did not try GraalVM because I simply did not get to it in time.
Okay, thank you.
Okay, so there's another question on the monitor. Do you have any idea of how well does the JIT optimizations with the warm-up fare in serverless functions? I'd assume that once it spins down, you lose the benefit. So I don't know about the concrete implementations, but I assume unless they cache something, you lose all the optimizations. Maybe there's like some kind of federation of the JVM in the background, but I imagine that's a security hole. So uh, I did not try to benchmark it at all. Okay, thank you.